Hello everyone. In this video, I will talk about some practice problems for 2D kinematics. The first question. The horizontal coordinates of a drone in a strong wind are given by x equals negative 10t plus 3t squared and y equals 9t minus 2t squared. So notice that we do not consider the z direction. In reality, there must be a z component, right, for the drone to going up and down, but we do not have that. Where x and y are in meters and t is in seconds. So in other words, all the quantities are in SI unit. Question A. What is the velocity of the drone at t equals 2 seconds? Give both its magnitude and direction. And question B is the same question about the acceleration at t equals 2 seconds. Now, since we have x and y's expression in terms of time, t, then we can simply just plug in the time t equals 2 seconds in these two expressions. Then we will get to the position. We don't actually need that because the question is about the velocity, but it's just that you can do that, right? If you plug in t equals 2 seconds. But now let's do the take the derivative here. So the velocity's x component is given by the derivative of x with respect to t, and we have negative 10 plus 6t squared, 6t, no square. And at t equals 2 seconds, Vx equals, plug in 2 here, so we get 2 meters per second. Now for y, Vy, which is dy dt, equals, if I take derivative here, I get 9 minus 4t. Okay, so again, at t equals 2 seconds, Vy at 2 seconds equals 9 minus 8, which is 1 meters per second. Now question B, the acceleration is the second derivative of the position vector or the first derivative of the velocity vector. So let's start from the velocity here. Now ax equals dvx dt equals 6, okay, without any other t dependence. So we have 6 meters per square second. Remember, everything is in SI unit, so we just need to write down the SI unit for the acceleration. Then that's it. Okay, so dvy dt equals, now we have negative 4. Let's start from here, meters per square second. Okay, and we can see that the ax, ay, they are constant. They do not depend on the time. So that will include t equals 2 seconds. Okay, so at these 2 seconds here, we also have the same value. Okay, so now let's draw a picture of the two vectors and see that relation, and then we can apply the knowledge that we have from this chapter to talk about its last question here is about the motion. What's drone's motion? So here's the Cartesian coordinate I can build x and y. Now for Vx and Vy, we have 2 and 1. Now let's say here is approximately 2. Then 1 is half the value. Then we have the velocity here. So velocity vector is roughly like this. But of course, you can you need to change the coordinate here to vy and vx, right? All right. So now let's draw the ax, ay. So ax is 6, ay is -4. So 6 is about, let's say it's probably here. Then in this case, you want to say the coordinate system here is ax, ay. So the acceleration direction is roughly like that. That's A. And then if we apply our discussion earlier, right, V and A, they have this relation. A's component along the velocity is in the same direction as the velocity. So let me quickly draw this projection of the A to the direction of V. So that's approximately the A parallel component, and that the perpendicular component of A. So I'm gonna say that in this case is speeding up. At this instant is speeding up and turning right. Okay, it's turning right. So that's the motion of the drone at this instant. Second question. A package is dropped from an airplane that is traveling at 200 meters per second horizontally at an altitude of 5,000 meters. Question A, how long does it take the package to hit the ground? How far has the package traveled horizontally? Now that is a classic projectile motion problem. And let me first set up the coordinate system, and then we can solve this problem using that system. So I'm going to draw horizontally the x-axis, and usually the vertical direction is upward is the positive y direction, but it doesn't matter. I'm going to use the downward direction as the y-axis. Okay, so again, it doesn't matter. You just need to pay attention to the positive direction and then the acceleration direction and velocity direction, then will change accordingly their sign according to that. Okay, so at the beginning, the package is here, right, at the origin, and then its initial velocity is horizontal. V naught equals 200 meters per second, and it's positive, right, because it's along the positive x-axis. And in the y direction, there's no velocity. Actually, let's write down these known quantities. At t equals 0 second, we know the coordinate. And the velocity, the x component is the velocity, initial velocity. V naught y equals 0. The ax is 0. That's no horizontal acceleration, but in the y direction, we do have the gravity, right? Gravitational acceleration, positive g. The reason it's positive is because it's in the same direction. That's ay, okay, equals positive g, same direction as the y-axis. And when we do the numerical calculation, we want to put in plus 9.8 meter per square second. Okay, so these are the known quantities, and then we're going to write down like two set of the kinematics, one set for x direction, second set for the y direction. And actually, let's do that because I need to figure out the instant the package hit the ground. Okay, so now let's say the ground level is here. And it's 5,000 meters in the y direction. Then let me draw the package trajectory. It's like that. And then we need to figure out this instant t. What is this instant? So we have these 5,000 meters information for the final position. So let's write that down. So y equals y naught plus v naught y times t plus 1/2 ay t squared. Okay, but we can see that y naught equals 0, v naught y equals 0, so there are no contributions from the first two terms. The only contribution here is from the third term. Now from there, I can say t is given by square root 2y over g, and y is this y here. Okay, so that's the y final, which is 5,000 meters divided by 9.8. And we can figure out that the instant here is 31.9 seconds, almost 32 seconds. So that's the instant that it hit the ground. So that's question A. Second part of question A is that how far has the package traveled horizontally? Now the horizontal displacement here, let me call these x. That's also the coordinate of the final position in the horizontal axis. So x equals v naught x times t. Okay, because there's no acceleration in the x direction, so the package is going to do uniform motion in 1D, right, for the x direction. So we have 200 meters times 31.9 seconds, and it gives us 6,380 meters. Question B, what is the velocity of the package, both magnitude and direction, when it hits the ground? So we know the instant it hits the ground, Vx is still the original velocity, the initial velocity. So it's 200, still 200 meters per second. Now the y direction will be different. So you're going to get the acceleration ay times instant t, and it's actually gt. So we have 9.8 times 31.9 seconds, and it gives us 312.6 meters per second as the final velocity's y component. So the magnitude of the final velocity is this expression, and then let's plug in the numbers. And the answer here is 371 meters per second. But we also need to figure out the direction. So to do that, I want to draw the Vx and Vy schematically in this picture. So Vx is horizontal, and Vy is longer than Vx, right? So because it's 312. And their summation is given by this vector. That's the v. That's the final v that we calculated here. And its direction, let's say this angle is theta. Then we can calculate tangent theta equals Vy over Vx equals 312.6 over 200. And then we can calculate the inversion of that function. The angle here is roughly 57.4 degrees. Okay, so you can say from this picture, that's the ground level. There's a ground level, the direction, horizontal direction. So it's 57.4 degree below the horizontal direction. Okay, so that's what we say about the direction of the final velocity. Now question 3. A worker's power drill spins at 5,000 RPM. Now, what is the speed of a point on the rim of the drill bit of radius 0.5 centimeter? Now we know the 5,000 RPM is the angular speed, and it's not in SI unit, but we do need SI unit for doing the later calculations. So let's change this RPM to radian per second. Okay, so RPM means revolution per minute. So one revolution is 2 pi, right? So let's multiply 2 pi radian and divided by 60 seconds. So that will give us the radian per second as the unit. Okay, so if we calculate this, it gives us 5.236 times 10 to the second radian per second. Okay, and the reason I keep a lot of digits here because this omega here is an intermediate number, and you don't want to let it affect the final answer. So let's keep a lot of digits here. Now we can do the calculation of the speed. So here's the picture. That's the drill bit, and radius is r, and then it rotates with omega angular velocity, and then we want to calculate the speed at a rim. Okay, so according to the linear and angular velocity relation, we know V equals R omega. R is 0.5 centimeter. So let's convert that into SI unit in meters. Multiply this number that we just calculated. Okay, now the final answer here should be in SI unit, and it turns out to be 2.6 meters per second. Okay, so meters per second is the SI unit for the velocity. What is the magnitude of the radial acceleration of a point on the rim of the above drill bit? So we're looking at the radial acceleration here. Let's call this AR. Okay, so AR, according to the lecture, we know it's R omega squared. Again, R is this number. Omega is 5.236 10 to the second, and then we square it. And that equals, number here is 1.4 times 10 to the third meters per square second. Okay, so that's a huge acceleration on the rim. Okay, but also you can calculate this using v squared over r, and v is this number here. But in order to do this calculation, you want to keep a lot of digits here as intermediate result, and then you want to put it here. Okay, so more digit here and then r here. You should get the same answer. Question 4. A car accelerates at 3 meters per square second from rest in a circular track with 100 meter radius. Question A. What is the speed of the car at 8 seconds? So first, we know whenever we talk about a car's acceleration at some value, and that value actually refers to the tangential acceleration, at. It's actually at, and the speed of a car can only be changed by the tangential acceleration. Okay, so at is 3 meters per square second. Okay, so that's from the question. Now, since we know the time instant is 8 seconds, so we can calculate v at this instant equals 3 times 8, 24 meters per second. Okay, so that's the velocity magnitude or speed at that instant. What is the tangential radial and total acceleration of the car? Again, tangential is the same as before. It's actually has a constant magnitude. Okay, so it's still this number. Now, in order to calculate radial acceleration, remember it's given by v squared over r. Okay, and v is this 24 that we just calculated, and r is 100 meters. And they give us 5.76 meters per square second. Okay, so that's the AR. Now the total acceleration is the summation of the two. So its magnitude is AT squared plus AR squared. And for AT we have 3. For AR we have 5.76 squared. And that equals 6.5 meters per square second. Okay, and you can also visualize this A. So let's say here is the circular track, and here let's say it's at t equals 0 second. Okay, now at this instant there's only or actually the velocity should be 0, so that's nothing here. And at t equals 8, let's say it's here, then the velocity is this way. Okay, and let me use a different color for acceleration. So acceleration is also along, at is also along this direction. But now that's an AR, which is actually bigger than AT. Okay. Now at the beginning, I also want to put in the acceleration. The acceleration is tangential, and it only has this component, and there's no AR here. Okay. All right. So these are the practice problems for the 2D kinematics. Thanks for watching.